Hi, welcome to a very important lesson. Just kidding. Okay. Alright, so that was just voltage again, because it's super important. We learned 2 lessons ago that voltage is energy or change energy or work per charge. We also learned last lesson that current is charge flow in a certain time. So those are both important ideas. Today we're going to relate these 2 ideas together. If you want to take a guess, how might they be related? If I increase V, will I increase, decrease, stay the same? What do you think? Okay, we're gonna watch a video.
Start by sitting a cup full of water on a block and an empty cup on the table. Position a hose so that it connects both cups. I colored the water to make it easier to follow this process. To start the siphon, we need to fill the hose with liquid. To do this, insert a pipette into the hose. Squeezing the bulb forces air out of the tube, creating bubbles. Slowly releasing the bulb, we see liquid moving into the tube. We might say that the pipette is sucking liquid into the tube. Actually, the liquid is being pushed into the tube by the external air pressure. When we release the bulb, a partial vacuum appeared. External air pressure pushes water toward this vacuum. To start the siphon, remove the pipette while holding the end of the tube below the level of the liquid. It is important to keep this end of the tube below the liquid level, or the liquid will run back into the upper cup. Once started, the liquid will continue to flow. One of the surprising things about this is that the liquid actually flows uphill as it exits the upper cup. This process requires both air pressure and gravity. If we look at the siphon in its start position, we see that the column of liquid in the tube on the left is much shorter than the column of liquid in the tube on the right. The column of liquid on the right is heavier than the shorter column. Pulled by gravity, it starts to fall, flowing towards the lower cup, pulling water from the upper cup with it. This flow continues until one of 2 things happen. Either the liquid is all removed from the upper cup, or an equilibrium is reached. This occurs when the liquid level in each cup is the same. This siphon has stopped flowing. Equilibrium has been reached. The level is the same in each cup. When the siphon starts, the long column of liquid weighs more than the short column. When the 2 columns have the same vertical height, forces are balanced and the flow stops. Sitting both cups on the tabletop, we can see the siphon starting to flow, stopping when both cups are at the same level. There is another question. Why does the column of water stay together? Why doesn't it liquid level run back? One of the surprising things about once started.
Okay, so this is a lesson where it'd be really easy to teach you if you understood siphons. But since you don't, I'm just going to teach you guys siphons first, then we'll teach you about V and I and whatever. So, first question. If there's 2 cups, like this in the video, we saw that fluid will flow from the higher cup to the lower cup. So pretty easy question. How does the energy of the water in the higher cup compare to the energy of the water in the lower cup? And let me clarify it. It's potential energy. How does the potential energy of the water here compare to the potential energy of the water here? What do you think, Daisy? The higher cup has more energy. Yeah, that's right. Since gravitational potential energy is mgh, height, the higher cup has more energy. But is that just because the higher cup has more water? What do you think, Hazel? No, the higher cup has more energy per amount of water. Yes, very good. Because UG is mgh. It depends on G, H, and M. Yeah, the higher cup will have more energy if it has more water. But even if they have the same amount of water, let's say there's 1 kilogram of water in the top cup and 1 kilogram in the bottom cup, the top cup will still have more energy because M is the same, H is higher. The higher cup has more energy per water, energy per amount, energy per charge. This is analogous to voltage. A higher cup is a higher voltage. A lower cup is a lower voltage. The difference in height is the potential difference. So that's good. All right. If the height of the cup is analogous to V, what's analogous to I? Yes, Sage? The speed of the water. Excellent job. Hooray. 3 smart babies. And also a lot more over there on the side of the screen too. The speed of the water is analogous to the current. Watch the video, tell me what determines the speed of the water flow. Look at the speed of the water flow right now. Look at the speed now. Look at the speed now. Wow, it's so slow. The guy's gonna cut the video. Right about... Just kidding. Look at the speed. Look at the speed at the start. Look at the speed here. And then when the levels are very close, what happens to the speed? We know they're going to stop when the water levels are equal. But what's the speed as that approaches equal? That's the question. What determines the speed of the water flowing through the tube from cup to cup? Yeah, great job. It was the difference in level. The difference in height, the potential difference, the voltage, affects the flow of water. And that is true too for electrical currents, electrical circuits, charges. The voltage is provided by a battery. And in physics circuits, you always have wires that perfectly transmit current with no energy loss. And you must have a resistor or a light bulb. If you don't have a resistor or a light bulb, your circuit will overheat. It's called a short circuit. It's going to explode. It's bad. Don't do it. So you must have a resistor. As we saw, the higher V, the higher I. Most batteries are pretty low voltage, like only 1.5 volts or 1.5 joules per coulomb. They'll make a very low current. So if I have a much higher voltage, like 15 volts, 10 times the voltage, I'll probably get around 10 times the current. The speed the water travels through the tube depends on the height. It depends on how much energy you have at the top and how much less energy you have at the bottom. This is the same. The speed that current flows out of the battery through the resistor and back into the battery depends on how much more energy the charge has at this side than at this side. So V is proportional to I. It's based on one last property of the resistor. That property of the resistor, pretty straightforward. It's called the resistance, R. The resistance R is a property of the resistor. It's how good a resistor it is. Since V is in volts or joules per coulomb, and I is in amps or coulombs per second, we get some very weird units. That means resistance. Let's say I have like the number I gave was like 115 volts. Let's keep it easy. Let's say I have a 3 amp current from a 15 volt voltage. R must be 5. It's 5 joule seconds per coulomb squared. Also known as a joule is a kilogram meter squared per second squared. So the seconds cancel. Oh, much better. It's 5 kilogram meters squared per second coulomb squared. Is that better? No. Resistance for this circuit, 15 volts over 3 amps, is 5 ohms. OHMS. Of course, we can't use capital O because that looks like a 0. So we use 5 omega for 5 ohms. 5 ohms is 5 volts per amp in the most simple terms. It's also this and this, but this is like gibberish. It's 5 volts over amps. For every amp of current, we need 5 volts of voltage through a 5 ohm resistor R. So yeah, in that analogy, in that video, the difference in height affected the speed of the flow. The higher the high cup and lower the low cup, the faster the liquid flowed. But what else affected the flow? The tube. The tube has a property called the resistance. What about the tube affects its resistance? So what properties of the tube will determine how fast water flows through it? Tell me right now. What about the tube could tell me the speed of flow through it? Any ideas at all? Just brainstorm, tell me what might affect the speed of flow through the tube. There are lots of good answers for this question. A big one is length. A long tube will take more time to flow through. It'll be harder for fluid to go through. If you want to get the liquid out fast, you need a short tube. So length of the tube. Another one is the area of the tube, the width of the tube. Basically for this area, you take the tube, you chop it in half or whatever, and you look at the circle, find the area of that circle. If I take the tube and I break it in half, this area is known as the cross-sectional area. That's the area. The bigger the cross-section area, the wider the tube. So it's basically the wideness of the tube. And there's one last factor that affects resistance in electricity, but not really in fluid flow. If you use a plastic straw or you're more environmentally conscious and using a metal straw, good for you. It probably doesn't affect the speed at which you're drinking like water or like milkshakes. But you might think that like a milkshake takes longer to drink than water. For electricity, it's always the same thing flowing, electrons. But instead of the thing flowing, the material that's being flowed through affects the resistance. Metals like copper and iron have very low resistance. Non-metals like plastic and wood have very, very, very high resistance. Usually we assume that metals have no resistance at all, and non-metals like wood have infinite resistance. That's not really true. There's a factor called resistivity that depends on the material. I'll show you guys the table of resistivities in class. It's not super, we're not going to spend that much time on resistivity. It's like a recent topic. But it's a material property based on the material, like iron, copper, gold, and also the temperature of that material. This is a rho, not a p. It's a sideways lowercase Greek r because we can't use r, so we got to use the Greek one instead. So this is rho, resistivity. So some materials have a high rho, some have a low rho, and they also depend on temperature. Take a quick guess. What will have a high resistance? A warm material or a cold material? Just take a guess. Okay. Some people say that, oh, well, a warm material, the atoms are moving faster, so the electrons are moving faster. So that'll be low resistance. It's the reverse. If a metal is like warm, the atoms are vibrating. If the atoms are vibrating, they're going to block the electrons more. So a warmer material will have a higher resistance. And that will actually, we'll come to this later, that'll actually make it give off more energy. And if it's a light, it'll be brighter. Um, Sometimes lights take a little bit of time to warm up, and that's why. You might not have seen this in real life very often, but it's true. Here's like a video of like some gym lights being turned on. Probably when you go to gym, usually the lights have been on for hours, but see here. It starts out dark when they first turn the lights. The lights are on, they just are cold and not working very well. Then as time goes on, the lights get brighter and brighter and brighter. And finally, you can actually see where you're going because the lights took a lot of time to warm up. Not super relevant, but it's true. Um, anyway, this is the main idea. It's called Ohm's law, OHM law, V equals IR. You can also say I equals V over R, or R equals V over I. That's fine. These are all forms of Ohm's or Ohm's law. And it's the same ohm, that gave his name to the units for resistance, ohm. 1 ohm is 1 volt per amp. So 3 important equations to describe a circuit. In this circuit, V equals I times R. If I have a 15 volt voltage and I'm getting 3 amps of current from the battery, from the 15 volt battery, the resistor connected must be 5 ohms. I'll come back to this exact picture in like 5 seconds for me, but a day or two for you.